The science behind algorithm analysis, understanding efficiency in code execution in today's fast-paced digital world, where milliseconds can determine success or failure, understanding how algorithms perform is crucial. From search engines indexing billions of web pages to social media platforms delivering personalized content, efficient code execution underpins every modern application. This deep dive explores the science behind algorithm analysis. At its core, algorithm analysis involves evaluating an algorithm's efficiency in terms of time complexity and space complexity. These metrics help developers choose the most optimal solution when faced with competing approaches that solve the same problem. Fundamentals of time complexity. Time complexity quantifies the amount of computational time an algorithm requires relative to the input size. It focuses on how runtime increases as datasets grow larger. By analyzing these relationships, we gain insight into which algorithms will scale better under different conditions. This measurement helps identify bottlenecks before implementation. For example, an O(n) superscript 2 sorting algorithm may work fine for small datasets but become impractical for large inputs due to exponential growth in computation time. Big O notation, the standard method for expressing upper bounds on runtime. It describes worst-case scenarios by ignoring constants and lower-order terms. Best versus worst case. Algorithms often have varying performance depending on input characteristics. A perfect case might be O(1), while real-world situations typically involve average cases closer to O(n). A solid grasp of Big O notation enables programmers to make informed decisions during development cycles. It allows them to predict scalability issues early without writing actual implementations first. Certain common complexities dominate many applications. Constant time operations remain unaffected by input sizes, linear time grows proportionally, logarithmic functions increase slowly, quadratic times escalate rapidly, and factorials represent extreme inefficiencies that rarely appear outside theoretical contexts. Space complexity considerations. While time complexity measures execution speed, space complexity evaluates memory usage requirements. Both aspects are critical components of overall algorithm evaluation since excessive memory consumption can lead to system crashes or significant slowdowns through swapping mechanisms. Determining space needs involves examining both auxiliary storage and the original data structures involved. Auxiliary space refers specifically to extra memory used beyond initial input parameters. For instance, recursive solutions often consume more stack space than iterative ones because each function call adds overhead onto the call stack until reaching base cases. This trade-off becomes especially relevant when dealing with limited hardware resources. Some problems require careful balancing between time and space considerations. Hash tables offer quick lookups at potential expense of higher memory footprints compared to binary trees which use less space but take longer for searches. Understanding these trade-offs allows engineers to tailor their choices according to project constraints and expected workload patterns. Memory limitations may force prioritization towards space-efficient techniques even if they sacrifice some temporal efficiency gains. Analyzing common sorting algorithms. Sorting forms one of the fundamental pillars upon which much of computer science rests. Different sorting methods exhibit distinct behaviors regarding time and space efficiencies, making comparative studies particularly insightful. Bubble sort exemplifies simplicity at the cost of poor performance, featuring O(n) superscript 2 time complexity in both average and worst-case scenarios. Its ease of understanding makes it popular for educational purposes despite being unsuitable for production environments handling substantial volumes of data. Insertion sort shares similar properties with bubble sort yet performs slightly better on nearly sorted arrays thanks to its adaptive nature. Still, it remains inefficient for unsorted collections containing thousands or millions of elements. Merge sort guarantees stable O(n) log n performance across all cases through divide and conquer strategy. However, its requirement for additional memory during merging phases introduces increased spatial demands compared to other alternatives. Quicksort provides excellent average case performance with randomized pivot selection, reducing likelihood of encountering worst-case scenarios. Nevertheless, its vulnerability to maliciously crafted inputs necessitates cautious implementation practices. HeapSort maintains consistent O(n) log n behavior regardless of input order via heap structure manipulation. While generally slower than Quicksort in practice, it ensures predictable results free from pathologies associated with certain pivot strategies. Asymptotic notation explained. Asymptotic notation serves as mathematical shorthand allowing precise descriptions of algorithmic behaviors as input sizes approach infinity. Three primary notations define boundaries within which performances lie: big O, omega, and theta. Big O establishes upper limits indicating worst-case runtimes. It abstracts away constant factors focusing solely on dominant terms affecting scalability trends. Omega represents lower bounds signifying best-case scenarios. Unlike Big O, it indicates minimum possible execution times rather than maximums. Theta combines both perspectives, forming tight bounds around algorithm performance where exact asymptotic rates apply consistently irrespective of particular instances encountered. Selecting appropriate asymptotic expressions depends heavily on context-specific goals. Performance-critical systems benefit from knowing absolute ceilings, whereas security-focused analyses prioritize establishing minimal guaranteed response times. Accurate representation using correct symbols prevents misinterpretation among peers reviewing source materials. Misapplication could lead to flawed assumptions about what constitutes acceptable scaling capabilities under various circumstances. Empirical versus theoretical analysis methods. Evaluating algorithms entails two complementary approaches: empirical testing and theoretical modeling. Both provide valuable information, albeit serving somewhat different objectives within broader software engineering processes. Theoretical analysis derives conclusions based purely on mathematical formulations independent of any physical computing environment. This approach offers generalizable insights applicable universally across diverse architectures and configurations. Empirical measurements rely on concrete experiments conducted under controlled settings utilizing benchmark suites designed to stress test candidate solutions against known standards. Combining these methodologies yields richer understandings of practical implications versus idealized predictions derived solely from abstract models. However, pure theory sometimes fails to account for real-world anomalies such as cache effects influencing actual speeds differently than predicted equations suggest. Conversely, empirical data alone lacks predictive power for future expansions beyond tested ranges. Therefore, responsible practitioners adopt hybrid strategies incorporating elements from both domains, ensuring robustness against unforeseen challenges arising later stages after deployment. Design patterns influencing algorithm efficiency. Certain design principles significantly impact how efficiently algorithms operate within given constraints. Recognizing these patterns empowers developers to craft optimized solutions tailored precisely toward desired outcomes. Divide and conquer breaks complex problems down recursively into smaller subproblems whose individual resolutions contribute collectively toward final answer. Classic examples include merge sort and quicksort demonstrations earlier discussed. Dynamic programming stores intermediate results, preventing redundant computations typical in naive recursive implementations. Fibonacci sequence calculation illustrates this well, showing dramatic improvements over straightforward recurrence relations. Greedy algorithms make locally optimal choices aiming toward global optima, although there exist notable exceptions where greedy selections fail, producing globally optimal answers. Backtracking systematically explores possibilities, eliminating unpromising paths early, thereby pruning vast portions of search spaces effectively. Branch and bound extends backtracking further, introducing bounding functions helping discard entire subtrees deemed incapable of yielding improved solutions compared current best found thus far. Optimization techniques through amortization. Amortization distributes costs unevenly across multiple operations, allowing seemingly expensive actions to occur infrequently enough so their aggregate impact remains manageable within acceptable Performance thresholds. Consider hash table insertions requiring occasional resizing operations, increasing underlying array capacity. Although each resize operation incurs O(n) cost, frequency decreases exponentially, leading overall insertion rate remaining O(1) amortized time complexity. Similarly, dynamic arrays automatically expand when full, facilitating seamless addition without needing pre-allocation of potentially wasted space ahead of time. These optimizations demonstrate how smart architectural choices enable maintenance of high-level abstractions while still achieving desirable efficiency levels suitable for majority of real-world applications. Amortized analysis proves particularly useful when assessing data structures exhibiting irregular operation profiles rather than uniform distributions commonly assumed in simpler theoretical frameworks. Practical applications across industries. Algorithm analysis finds extensive applications spanning numerous industries, transforming raw computational ideas into tangible benefits realized daily by users worldwide. Search engine optimization leverages sophisticated ranking algorithms capable processing massive index corpora, simultaneously delivering highly accurate query responses within fraction seconds. Financial institutions utilize risk assessment tools grounded in Monte Carlo simulations, enabling rapid scenario evaluations essential maintaining stability amidst volatile markets. Healthcare professionals employ diagnostic imaging technologies enhanced through advanced pattern recognition techniques, identifying subtle abnormalities in visible human eyes alone. Logistics companies optimize delivery routes, continuously adapting dynamically changing traffic conditions, maximizing fuel economy, minimizing travel durations. Entertainment sectors harness machine learning-powered recommendation engines, personalizing user experiences, fostering engagement, enhancing retention metrics, critically important, sustaining revenue streams. Evolving landscape of algorithmic research. Continuous advancements drive ongoing innovation, reshaping landscape algorithm research, opening new frontiers, exploration previously unattainable through conventional means. Quantum computing promises revolutionary breakthroughs, solving currently intractable problems within reasonable timeframe, exploiting superposition entanglement phenomena, defying classical paradigms entirely. Neural networks-inspired artificial intelligence models achieve unprecedented accuracy, surpassing traditional statistical methods, demonstrating remarkable adaptability learning capabilities. Blockchain technology introduces novel consensus protocols, ensuring secure decentralized transactions, challenging existing centralized infrastructures, prompting re-evaluation trust management mechanisms. Data stream processing frameworks address ever-increasing velocity, volume, variety, big data ecosystems, developing specialized algorithms capable operating limited memory resources. Edge computing initiatives push compute-intensive tasks closer end devices, reducing latency, improving responsiveness, creating opportunities, designing lightweight, distributed solutions. Conclusion: algorithm analysis stands as cornerstone discipline guiding development decisions, shaping performance characteristics, ultimately determining viability deployed solutions. By mastering fundamentals surrounding time/space complexities, leveraging appropriate analytical tools, practitioners ensure creation scalable, maintainable systems ready face evolving technological landscapes ahead.